Hello students, in this section or rather in this episode we will discuss another very important application of Gauss theorem. So in this section we will discuss or rather we will try to find an expression for the electric field at a point due to a uniformly charged solid sphere. Now in the previous episode we have discussed electric field due to a uniformly charged spherical shell, where the charge is uniformly distributed over its area. It's a two-dimensional case. Here we will consider the charge to be uniformly distributed throughout the volume of the charge sphere. So it's a three-dimensional case. So here we will be making use of the term rho, which is volume charge density, which is defined as charge per unit volume. So in order to proceed with the article, we will consider a sphere, say of radius capital R, and let charge small q be uniformly distributed throughout its volume. So it's a three-dimensional case. So volume charge density is given by charge per unit volume. Volume of the sphere is 4 by 3 pi r cube. So the charge would be 4 by 3 pi r cube multiplied by rho. Let's put this as equation number 1. So our objective would be to determine the expression for the electric field at a point when it lies outside the uniformly charged sphere. Then in subcase 2 we will consider the observation point to be lying on its surface, and in the third subcase we will consider the observation point to be lying inside the uniformly charged sphere. So let's start with case 1. Case 1 is when small r is greater than capital R. Small r is considered to be the distance of the observation point from the center of the uniformly charged sphere. Suppose this is the observation point where we intend to determine the expression for the electric field, right? And this point O is the center. Now this is a complicated situation. We have to make use of Gaussian theorem so as to obtain the expression for the electric field. And in order to apply Gauss theorem, we need to consider a Gaussian surface, right? So here it is preferable to consider a spherical Gaussian surface. So taking point O as center and OP is equal to small r as radius, we will consider a spherical Gaussian surface passing through point P, like this. This is imaginary one, so it has to be represented by dotted lines. Now this is a Gaussian surface enclosing net charge Q. We can very much make use of Gauss theorem over here. The Gauss theorem states that electric flux, which is given by the closed surface integral of the electric field, is numerically equal to 1 by epsilon times the net charge enclosed. Here the charge enclosed is Q, the entire charge. ds, that's the area vector of the Gaussian surface. So this is the Gaussian surface. Consider any elementary portion. Its area vector would be in the radially outward direction, perpendicular to the surface, isn't it? And electric field due to this positive charge would also be in the radially outward direction. So the direction between the electric field and the area vector is same. I mean they are parallel. So the angle between these two is 0 degree. So what we get is E ds cos 0 it is equal to Q by epsilon. Now look, electric field at any point on the Gaussian surface being equidistant from the center will be constant. Therefore, E can be taken outside the integration. And integration of ds, if we add these small areas, that will give us the total surface area of the Gaussian surface, which in this case is 4 pi small r square. So that's the surface area of the spherical Gaussian surface. Cos 0 is 1. So we obtain Q over 4 pi epsilon r square. Now look, this is a familiar formula. This is actually the magnitude of the electric field due to a point charge. So what's the conclusion basically? If the observation point lies outside the uniformly charged sphere, then this sphere may be treated as a point charge. That is, in such a scenario, the entire charge on this sphere may be assumed to be concentrated at its center. So that's the conclusion. Now let's find the expression for electric field in terms of rho. So we simply need to substitute the value of Q from equation 1 in equation 2. So we get 4 by 3 pi capital R cube rho divided by 4 pi epsilon R square. So 4 pi get cancelled, we'll be left with, okay, this will be the expression and R square will be also there. So electric field at a point outside the uniformly charged sphere would be given by rho R cube divided by 3 epsilon R square. So this is the expression for the electric field at point P. Now you can check, this term is constant, isn't it? So with distance, electric field varies as 1 by R square. This will be particularly important when we plot graph showing variation between the electric field and the distance of the observation point from the center of the uniformly charged sphere, right? So we need to consider this into account while plotting the graph. So this is the expression. Now case 2. Case 2 is relatively simpler. I mean, you need not to derive these equations time and again. Case 2 is when the observation point lies at any point on the surface. So obviously, in this case smaller, it will be equal to capital R. So we are dealing with this case, right? So at any point on the surface, the electric field would be given by the same expression. Simply substitute the value smaller as capital R. If you substitute the value smaller here as capital R, so R cube by R square will be left with capital R, isn't it? So we will get rho capital R divided by 3 epsilon. So this is the expression for the electric field at a point on the surface of the uniformly charged solid sphere. Now you can check, the entire term is constant. So it is constant maximum value. So it is constant maximum value. So that's an important conclusion. Due to a uniformly charged solid sphere, the electric field at a point on its surface is maximum. This is what we have derived from subcase 2, right? Now the third and the final case is left. In this case, we will consider the observation point to be lying inside the uniformly charged sphere. Suppose this is point P. So this is the distance of the observation point from the center. Again, in order to find out the electric field at point P, we will consider spherical Gaussian surface passing through point P of radius smaller. So in this case, we are dealing with this case. Smaller, less than capital R. Now look, this is a spherical Gaussian surface which must be enclosing some charge, which obviously would be less than Q. So let the charge enclosed by the spherical Gaussian surface is Q dash. So applying Gauss theorem on this Gaussian surface, we get electric flux, which is given by closed surface integral of the electric field. It is 1 by epsilon times net charge enclosed. In this case, the Gaussian surface encloses a charge Q dash, which obviously is less than Q. Here remember, the charge is distributed throughout the volume of the body. So this Gaussian surface will be enclosing some charge, which is considered to be Q dash over here, right? Now ds, this is again the area vector of the Gaussian surface, which will be in the radially outward direction. Electric field due to the positive charge will be also in the radially outward direction. So again the angle between these two is 0 degree, isn't it? So cos 0 is 1, so we will get E ds cos 0 is equal to Q dash divided by epsilon. Again, electric field at any point on the Gaussian surface being equidistant from the center, point O, will be constant, so it can be taken outside. Integration of ds. It will give us 4 pi into small r square. It will give us the total surface area of the Gaussian surface under consideration. Q dash. We can represent Q dash in terms of Q. How to represent it? Now look, this is the volume charge density, isn't it? So volume charge density is rho. Therefore, charge Q dash would be rho multiplied by volume of the Gaussian surface, which is 4 by 3 pi small r cube. So Q dash can be replaced by this. Look, rho is the volume charge density. In volume 4 by 3 pi r cube, the entire charge stored is small q. So in volume 4 by 3 pi small r cube, the charge content is Q dash, which will be given by volume charge density multiplied by the volume of the Gaussian surface under consideration. You can make use of the unitary method as well, so as to obtain this expression, right? So substitute the value of Q dash as rho multiplied by 4 by 3 pi r cube. So integration of ds, that will give us 4 pi small r square, which is the total surface area of the Gaussian surface. So we get 4 pi r cube 3 divided by 3 rho epsilon. 4 pi get cancelled. So we are left with, and this rho is also over here. So we get electric field at a point inside the uniformly charged sphere would be rho r square, and here it's r cube. So we'll be left with r 3 epsilon. This is the expression which we will obtain. So this is valid for r small than capital R. And you can well judge this term is constant. So electric field varies with distance small r as directly proportional smaller. Means with the increase in the distance, the electric field also increases. So at the center, when r equals to 0, electric field will be also 0. So as the observation point is moving towards the surface, the strength of the electric field will keep on increasing. At the surface, it will be maximum, and thereafter it will obey inverse van law, right? So these are the three important sub cases of this particular article. Now